Lecture for Chapter 2. For Chapter 2, we're going to also read all the sections. This chapter deals with atoms and molecules and ions, and the first part of it, which we're going to talk about right now, deals with the development of the atomic theory. How did we come up to believe what the atom is? What were the early beliefs of what the atom was and how it progressed? And then we're going to talk about how atoms combine to form molecules and then eventually how they form ions. But you will be responsible for reading all of the sections in Chapter 2. Here's a chapter outline. We're going to deal, like I said, with ideas in atomic theory and how they evolved over the centuries. Atomic structure and symbolism, so talk a little bit about the atomic number and the atomic mass, etc., and then the chemical formulas, how to write them, etc. So read sections 1 through 4. What is an atom? The word atom comes from the Greek word atomos, which means indivisible. This is because the early Greeks believed that all matter was made up of simple particles, subunits that were indivisible. You could not divide them any further, and they called that particle an atom. Now we know that the atom is not in the smallest indivisible subunit of matter. We know that there are smaller subunits than the atom, but at the time, that's what they believed because that was what technology allowed them to see. And it was much, much later that we started to understand what the atom was made of. But what led to the development of the modern atomic theory? There were several different observations and laws that came into play. The first one being the law of conservation of mass. This law was termed or coined by this gentleman over here, the French scientist Lavoisier, in 1787, and it states that mass can neither be created nor destroyed in a chemical reaction. What it does is simply changes from one form to another. And we know this to be true. For example, if we have hydrogen and oxygen combining to form water, we cannot lose a hydrogen or oxygen. They both combine in very specific ratios, which we'll cover in the next slide, to form water. And therefore, to have a complete chemical equation, we have to make sure that it has to be balanced. We have to have the same hydrogen atoms on both sides of the equation, the same oxygen atoms on both sides of the equation. We'll learn how to balance chemical reactions later, but that comes from this observation, from this law, that mass cannot be created nor destroyed, and therefore the atoms on the reactant side, on the left-hand side of the equation, have to be the exact same number as those atoms in the product side or the right side of the equation. So they simply change form, they recombine to change form and form different molecules. But we cannot add more atoms or remove more atoms. They have to be equal on both sides. The next law that contributed to the atomic theory is the law of definite proportions, sometimes called Proust's law after the gentleman that first termed it. We can also find it under the law of definite composition or the law of constant composition, etc. So all of these are synonyms of each other. They mean the same thing. It states that a given chemical compound will always contain component elements in a fixed ratio, and it doesn't depend on the source or how it's prepared. Which means that if I'm talking about a chemical compound like water, for example, since we mentioned water, water will always have hydrogen and oxygen mixed in a fixed composition, fixed ratio. There's always 2 hydrogens to every oxygen. And it doesn't matter how we prepare water. It doesn't matter where it's sourced. It can be in China, or it can be in Germany or in US. It doesn't matter where you find water. What makes water water is that it has two hydrogen atoms for every oxygen atom. So the ratio between the elements that make up that compound is always fixed, and that's what the law of definite proportion states. If I change that ratio, for example, if I look at hydrogen peroxide, which is H2O2, that means it has two hydrogens for every two oxygens instead of for every one oxygen like water does. That means that I have now changed the compound completely. I don't have water anymore. I have a different compound. So therefore, one chemical compound will always have its component elements, so whatever makes elements make it up, they will always be in a fixed ratio. If you change that fixed ratio, you have changed the compounds. This is called the law of definite proportions, or definite composition, or constant composition. The next gentleman who contributed to the atomic theory is Dalton. Dalton really kind of took what was there and he packaged it a little better, and he came up with his atomic theory, and here are the 4 points that he mentions. The first one, where all matter is composed of exceedingly small invisible particles called atoms. This postulate, well, comes from that first slide we talked about, the Greeks that named that indivisible particle atom. So he just reformulated it, or put it all together in one atomic theory. So point number 1 is that all matter is composed of atoms. Point number 2 is that atoms of an element, they have a given mass and a given property, and atoms of differing elements will differ in mass and properties. If I have copper metal, for example, and if I have aluminum metal, those atoms of these two elements will differ, will have different mass, and they'll have different properties. Copper is different, looks different than aluminum does. That's because its atoms differ in properties than aluminum atoms do. This is point number 2. So atoms of a particular element will be different from atoms of another element in mass and in their properties. The next point, atoms are not created or destroyed in a chemical reaction, they simply rearrange. This is the law of conservation of mass, Lavoisier's law. Once again, he didn't really come up with it, he just packaged it in one atomic theory, a cohesive theory versus one piece here and one piece there. And then the last point is the law of definite proportions, that atoms combine in simple fixed whole number ratios to form compounds. Just like atoms of hydrogen combined with atoms of oxygen to form my water in a 2-to-1 ratio, that is an example of the law of definite proportions. So let's talk about the atomic model and how it actually evolved from Dalton to the modern quantum theory of the atom, what we know today. It has changed through many, many times, and it has advanced. There's been several very key discoveries that have led to shaping of the atomic model and making it to what it is today. Well, the first experiment that kind of gave us an idea of some of the subatomic particles that the atom had was the J.J. Thomson and his discovery of the electron. At this time, so this is late 1800s, they still didn't know that the atom was divisible and that there were smaller particles than the atom. And then here comes J.J. Thomson, and he's doing these experiments with a cathode ray. So he he has high voltage here, passes high voltage, and the cathode, um, it emits these rays. And what happens is the rays, the cathode rays, if it's placed under a magnetic field, and also these plates that are charged plates, what happens is that they are deflected. So this ray is deflected and is deflected upward towards the positive plate that is charged here. If these were not charged at all, they would just pass through and they would not be deflected at all. They would continue straight. But they are deflected, and they're deflected upward towards the positive charge, the positively charged plate. Now, at the time, it was known that atoms, in general, atoms are not charged. They're ions are, but atoms themselves, so pure elements, are not charged. And so this ray that was coming from the cathode had to have particles that were not atomic particles, so they were not atoms. They must have been some different particle. And because it was charged, it was negatively charged because it was attracted to the positively charged plate. And J.J. Thomson, he named them initially the name corpuscles, but then the word electron stuck, and I'm actually glad that it stuck because it sounds much better than corpuscles. But he termed them. He named this particle the electron and said that this, from his experiment, concluded that these particles were negatively charged. Okay, so at this point we know that the atom has electrons, a negatively charged particle, so it can be subdivided. It has subparticles smaller than the atom. And because we know that the atom is not charged at all, these electrons have to be balanced out by a positive charge. But nobody knew what that was yet. Thomson had just discovered the electron. Now Robert Millikan came along, and he did this other experiment with little oil droplets. So he would atomize the oil, and the oil would be charged, and then he would observe it. He would put it between these plates that were electrically charged, and he could control the speed that these charged oil droplets could move through the air. He could immobilize them by adjusting the charge on these plates, and because of those, by adjusting the charge on the plates, he could figure out that all of these droplets were multiples of the same compound, or the same charge. And he figured out that the smallest charge, so all of these A, B, C, and E, are multiples of D. So if you take 1.6 times 10 to the minus 19th and you multiply it by 2, you get B, you get this charge. If you multiply it by 3, you get A and you get E. If you multiply it by 4, you get C, etc., etc. So all of these charges that he measured, the oil droplets, they were all multiples of this one charge. And the smallest charge was 1.6 times 10 to the minus 19th coulomb. And he postulated then that this was the charge of an electron. So they figured out that the charge of an electron is a negative charge, but it is this magnitude in coulombs. So now the electron was known, the subparticle was known, it was known to be negative, and it was known to have this particular charge. But still nobody knew what balanced the electrons out. The first model that was proposed was the plum pudding model, in which you have these electrons that are dispersed through this cloud of positive charge. And that is, you have one positive charge for one negative charge, but you have this cloud of positive charges, and then the negative charges are just kind of dispersed in the middle, kind of like a fruit cake model. It's called plum pudding because that's what they use in England. It looks just like this, or like an oatmeal raisin cookie or a chocolate chip cookie, where the chocolate chips are the negative charges, and then the electrons, and the cookie itself is the sea of positive charge. Well, there were some problems with that because nobody could figure out how to measure that positive charge, the sea of positive charge, and they should have been able to. So that was the initial issues that they ran into. And then Nagaoka, who was a Japanese gentleman, scientist, he came up with this view of the atom, where you have this really, really large central, if you will, now we know it's nucleus, but it was really, really large, where you have all of your positive charge concentrated in one ball, and then the electrons are orbiting around just like the rings in Saturn, for example. Well, the next experiment disputed both of these models, and let's talk about the nucleus. Actually, it was Rutherford is credited for it, but it was two of his graduate students that came up with this, worked on these experiments, and actually um, figured this out. But what he was doing is he had a radioactive source, and that would emit alpha particles, which are helium nuclei, and they're positively charged. So this beam of alpha particles was shot at a very, very thin gold foil, very, very thin. And then you had this luminescent screen that was all around it that would detect these scattered alpha particles by, if it hit over here, it would just illuminate it, and so you could see them. Now they found something that was very different than what they expected. Most of the alpha particles pass straight through the thin gold foil, and they hit the opposite side of the luminescent screen. However, some of them are slightly deflected, with some alpha particles completely deflected, almost coming back towards the source of alpha particles, so almost, not quite, but almost 180 degrees. Now, they formulated that if the first model of the plum pudding were true, that these alpha particles would just pass right through. There would be none deflected because the positive charge would be so diffuse that the alpha particles would just pass right through because they were small enough. But that's not the case. And they also formulated from this that there is a very, very small, dense core that is positively charged because it's repelling these alpha particles when they come very, very close to it. So if, let's say my nucleus was right here, is very dense and is very small, so most of the particles will pass around it. However, some will be deflected because they pass close to it, and they are deflected from the positively charged nucleus, repels the positively charged alpha particles. And then when they get really, really close to the nucleus, they get deflected almost 180 degrees. And that led them to believe that the nucleus is very small and very dense. So all of that positive charge is condensed in the center of the atom, and it has all of the positive charge in one place instead of in this sea of positive charge. The next two discoveries were also significant. Frederick Soddy discovered that elements, they can have different masses. These are isotopes. The same element can have a different mass. Well, that meant that you have to have another particle because we know that these positive particles are what make up an element. And if you change the number of positive particles, which are called protons, you will change the element. And therefore, for elements to have different masses, you have to have a third particle that is probably not charged. And that finally was discovered by Chadwick. He discovered the neutron, which accounted for the missing half of the mass in the nucleus. The electrons and the protons, that's what they were called, the positively charged particles, the protons made up about half of the half of the mass of the nucleus. The electrons have a very, very small mass, so most of the mass had to come from the other particles, but the protons, which were neutralizing the electrons because they're positively charged, they only made up half the mass of the nucleus. Therefore, there had to be another particle that wasn't charged, and Chadwick was the one that discovered it, and he named it neutron. And therefore, the current model that we have right now is this one, where we have, here's my proton in orange, and neutron. These two particles make up my nucleus, and then the electron orbits around the nucleus. And we will talk about how the electron orbits. It cannot orbit just anywhere like Nagaoka's model predicted. It has to be very specific where it is found. But this is the model for the current model of the atom that we have. We have the proton and we have the neutron, which make up the nucleus, very dense, the core of the atom, and then the electrons, which make up very, very a small part of the mass of the nucleus, and they orbit around the proton and the neutron. Here's the proton. It has a mass of 1.67 times 10 to the minus 24th gram, and a positive charge that is exactly the opposite of the charge of the electron. That's how they can balance each other. The neutron has almost the same mass as the proton, just slightly larger, and it has a charge of 0. The electron has a mass that is about 1,000 times less than that of the proton and neutron. So kind of insignificant compared to the protons and the neutrons' mass altogether. And then the charge is negative, but it's the same as the charge on the proton. This is the current model, and this is the one that you should be familiar with right now. We are now this will conclude part 1 of the lecture, and we are going to talk about the atomic number and the mass number in part 2.